Here's a question that we can try. A 12 centimeter length of wire carrying a 30 amp current is positioned between the pole faces of a magnet at an angle of 60 degrees as shown. So here's our 60 degrees right there. 60 degrees. So all we need to do is say, okay, talking about wire force from that magnetic field. It's just going to be I, L cross B. Or we can think of it as this ILB sine 60 degrees. Okay, let's plug it in. 30 amps of current. Our wire within the magnetic field is 1.12 meters. Again, so it's only within the length. So within, there's our 0.12. If you have a really long wire and the magnetic field's only passing a little bit, you have to only look at the segment that's passing through. Our magnetic field is 0.90 Tesla, the unit for magnetic field, and it's at an angle of 60 degrees. And the closer to 90, the greater the force. Plug it all in, we end up with 2.8 newtons. But then because it's a vector, we need to add in the direction as well. So what direction is going to go in? So we say, okay, we're going to stick our index finger first pointing the direction of the wire. So it's up and to the right. We're going to rotate our hand until our middle finger is pointing the direction of the magnetic field. And hopefully you can see, hopefully you're doing it with me right now, our thumb is pointing into the page right now. So the rod will actually experience a force into the page. Okay, so the rod will actually, if it's light enough, you'll actually see it, it'll actually move, or if it's not connected to anything. Okay, so here's another one. If we scroll down, so if we have a charge passing into a magnetic field, so this is really cool. We can combine some ideas from previous units. If I have a positive charge traveling into a magnetic field that is into the page, again, I'm going to get my right hand. My index finger is pointing to the right. My middle finger, in this case, is pointing into the page. You can see that the force is going to be up. So what's going to happen is as soon as that charge enters this field, let's get a red pen, it's going to start experiencing a force, and that's going to change the direction. So now the charge is going to be slightly moving upwards. But if you follow that path with your right hand, so the path is now a bit up and to the right. So what's going to happen is the thumb is going to then point a little bit up and to the left. And then it's going to point a little bit more and more. So what ends up happening is it experiences circular motion, because that force is always going to be perpendicular to both the velocity vector and the magnetic field. So it's really cool. We can actually combine circular motion with electromagnetism when we have a charge passing through a magnetic field. It's cool stuff. There's some really awesome applications that can develop from this concept. So let's see, if we had a positive charge, think of this as two separate questions. Let's do the positive charge first. This positive charge is moving to the right. When it hits there, magnetic field is out of the page. So my middle finger is pointing out. My index finger is pointing to the right. And my force points downwards. So it's going to loop around like that. For a negative charge, either you can use your left hand, or you can just use your right hand but then flip it around. If I'm using my left hand, my index finger points to the right, my middle finger is pointing out of the page, and my left thumb is pointing up. So it circles in that direction. The force is going to be perpendicular to it. So we can actually derive a new equation to actually learn more about this circular path that forms. So we know from previously, there's our magnetic force was given by the equation F is equal to QVB. So I'm going to ignore that cross product right now. I'm just going to write down here's a magnitude, F is equal to QVB. So there's our first equation. And hopefully remember from circular motion, or it's on your formula sheet, F is equal to, or for acceleration is v squared over r, and we can find the force by just multiplying by the mass. So if you have an electron traveling through, it's be the mass of an electron. If it's a proton, it'd be the mass of the proton. And now we can equate these two equations. Let's just think about the scalar quantity. I'm going to get rid of that arrow on top. Let's think about the scalar quantities. We're going to equate those forces together. We get QVB is equal to mv squared over r. And now if we rearrange this equation for r, we get r is equal to, so we're going to multiply both sides by r to do that. One of the v's cancel out, so we have mv divided by bq. And that gives us our radius of the circular path that the electron or proton will follow. Really cool stuff. So here is this next one is just a cool application of this concept. So this is combining both electric force and magnetic force. So it's a device called the mass spectrograph. So things like it's very important for identifying unknown objects or unknown substances. So this guy called Francis Aston, an English chemist, he invented the spectrograph. So how it works is, first, what we have is this, and we look at this diagram down here. Here's our diagram. So we actually need two magnetic fields. So first of all, what's going to happen is that you send some of the substance or whatever this unknown material is through this capacitor, these charged plates, first of all. So what's going to happen is that for the charged plates, if there's that positive negative, the positive negative plates are going to create a electric field. So what we're doing is we're sending a charged particle. So for example, you can ionize something and make it like positive or negative. So let's say we send a positive charge. So what's going to happen there is that this charge, if it's positive, as it passes through this electric field, it's going to be deflected upwards. So it's going to create a force upwards from the electric field. But at the same time, by creating a magnetic field that's perpendicular to this, it's going to create so this is, again, force from electric field. So force from electric field. At the same time, because the orientation of the magnetic field is going to create a force downwards caused by the magnetic field. And basically what we're doing here is we're creating a control. So what we need to do is, there's like millions of particles being traveled through, but we only want for control, we want very specific velocities of substances going in. So we can actually compare it to other things. So by having that known velocity going into it, so what's going to happen, so if the velocity of the particle is too great or too small, it's going to be deflected down or up. If we have that perfect velocity, so it's no longer unknown, we know it's going to travel through and enter into the second part. This is the mass selector. So the first part, we call it the velocity selector. Now it's in the mass selector. So now we know the velocity, and it's going to pass through this new magnetic field, which causes the charge to travel in a circular arc and hit what's called a photographic film. And depending on the mass, the arc will be smaller or bigger. So if it's lighter, it's going to have a bigger arc. If it's heavier, it's going to have a smaller arc. Oh, sorry, the other way around. So if it's bigger mass, it's going to have a bigger arc, so I meant to say. We can look at our equation again right down here. Right, so here R is equal to mv. So V is now known, magnetic field known, charge we give it at the beginning as known, so the only unknown is mass. So depending on where the substance hits the photographic film, we know the mass of it. And we use this to determine unknown substances. So for example, if you send cocaine through this mass spectrograph, it's going to create basically a thumbprint. And this is what the cocaine molecule looks like on the mass spectrograph. If you have other substances, it's going to create its own unique pattern as well. It's just like how your thumbprint can identify you from as someone else, like it can identify you as someone or someone else. This thing can identify different substances. Well, it's really cool stuff.